In these videos, you're going to learn how to use fuzz testing to locate unknown vulnerabilities in software. But before we get into the details, let's step back and take a look at the big picture so that you understand the critical importance of software robustness and security. In the world that we live in today, software is infrastructure. It permeates every aspect of our society, from devices you use every day, like a smartphone or a laptop, to the car that you drive or the smart TV that's in your home. The power that flows into your home comes from a power grid that depends heavily on software, and that in turn is supplied by power plants that also depend on software. Transportation networks, either trucks or trains or airplanes, are heavily dependent on software, and if you get sick and go to the hospital is full of medical devices and patient information systems, both of which are heavily software. Software as an industry is over 50 years old, but it's known for its unusually high rates of failure. Programmers are not known for writing bug-free code, but the general reliability of software cannot really be blamed on programmers, because even the best programmers will make mistakes, and it's really the process that surrounds those programmers that needs to improve. The consequences of software failures range from inconvenient to deadly. And in terms of these consequences, in light of these, a variety of adversaries have emerged that like to take advantage of vulnerabilities in software to do bad things. These adversaries have a wide range of skill sets and motivations. A casual hacker is really interested in the challenge or the thrill of the chase. A hacktivist group like Anonymous has a political or other type of agenda that they hope to further by causing software failures or other types of cybersecurity anomalies. Organized crime is obviously in it for the money, and cybersecurity is a very attractive arena for them. And then finally, nations have interests, either military or political, that they can use cybersecurity to forward. The one thing these different types of adversaries have in common is that they take advantage of software vulnerabilities to do the bad things that they do. So the real enemies here are software bugs or vulnerabilities. Who cares about these bugs? Well, basically everyone. But we see three main categories of people that care about vulnerabilities in software. The first category is builders. A builder organization creates software or puts software into some type of device or product. And for a builder organization, bugs that are found after that product release mean expense. So if a bug is found, the builder has reputation damage, which might not be able to be repaired. And in addition, they have to support their existing customers and fix the bug and issue patches. It's a very expensive process. In a perfect world, a world with unicorns, all builders would produce software that was almost defect-free. It would be very high quality. But of course, it's not a perfect world, and so we also see that there are buyers that are interested in software bugs. A buyer organization purchases software or devices or equipment and uses them to provide a service to their own customers. So a good example of a buyer organization is a network operator. A network operator buys switches and routers and other types of network equipment and uses them to create this network and sell the service to their customers. So if the products that they're buying are filled with defects and fail, it makes the buyer organization look bad and costs them money and reputation again. Another good example of a buyer organization is a hospital. A hospital's core business is helping people to get healthy, taking care of patients, and they buy medical devices and other types of information systems that they use to provide this service. And obviously, failures in software in medical devices can cause health problems or death, and failures in other types of information systems can cause loss of private data and other things that are very important to the buyer hospital organization. Finally, the third group of people that are interested in software vulnerabilities are the attackers. So the attacker can use a vulnerability to further their own gains, or they can just sell that vulnerability to somebody else for money. In software and in security in general, it's important to realize that there is no 100% security. You are never 100% safe. And a good example is a bank vault. It holds money. You don't want the thieves breaking in. And so you can make the walls really thick. You can put more locks on the door. But there's always a way to break into that bank vault. It's just a question of how hard it is to get in there. With software, it's basically the same thing. All software has bugs. All you can do is find and fix more of those bugs to make it more reliable and more secure. But you're not ever going to find all of the bugs. So what you're trying to do is balance the value of what you're protecting against the effort required to break it. So an analogy here is, imagine that I have a vegetable garden in my backyard, and if I'm worried about somebody stealing vegetables, I've got a certain type of adversary, and I can build a certain kind of defense against that adversary. On the other hand, if I buried nuclear missile launch codes in my vegetable garden, I'm going to have a different kind of adversary, and I'm going to need a different kind of defense. Let's take a closer look at software vulnerabilities, which come in three types. The first type is design vulnerabilities. The second is configuration vulnerabilities, and the third is code vulnerabilities. A design vulnerability occurs when the person who decided how the software should work didn't do a very good job. And a really simple example would be an online banking website that doesn't require user authentication. That's a design vulnerability, which is very easy for an attacker to exploit. A configuration vulnerability is something about the setup or configuration of a product that, again, is easy to exploit. So an example is a device that has default user credentials, maybe a username of admin and a password of admin. If the end user or customer for that product doesn't change those default credentials, it is a configuration vulnerability that, again, is very easy for an attacker to exploit. Code vulnerabilities are actual bugs or mistakes in the programming of the software. So a developer makes a mistake, which is a bug, and then when that bug is triggered, it causes the software to do something that it was not intended to do. These three types of vulnerabilities can be either known or unknown, where a known vulnerability is something that's widely known to everyone in the industry, and an unknown vulnerability is present but just hasn't been discovered yet. Obviously, the unknown vulnerabilities are much more dangerous than the known ones. The known ones you can build defenses for. The unknown vulnerabilities, if an attacker or other malicious person finds an unknown vulnerability and develops an exploit for it, then no one has any defense against that. There are tools that look for software vulnerabilities, and these tools are either reactive or proactive. Reactive tools look for known vulnerabilities, things that people know are bad already. One good example of this is the Nessus tool, which, for example, searches out for default user credentials on devices or systems. A proactive tool searches for unknown vulnerabilities, and a great example of that would be Codenomicon Defensics, which is what you'll be learning about here. So now let's zoom in on code vulnerabilities. A code vulnerability is really just a bug, which is a programmer mistake. So a developer made some mistake while they were writing this piece of software, and when that bug is triggered, it causes the software to do something that it wasn't designed to do. We'll talk more about this later, but software can crash outright. It might produce unexpected output. It might take an action that you weren't planning on or do something else unexpected. And regardless, it's a bug or a vulnerability because it's something that either the attacker can cause denial of service or they can possibly exploit it and take control. A bug is a bug is a bug, but it makes a big difference who discovers it. So if a product is released and it has an unknown code vulnerability in it, and an attacker discovers this and exploits it, then it's a serious security problem and causes a lot of expense and damages to the builder and the buyer involved. If instead the same bug had been caught and found by the software development QA team, the testing team, it could have been fixed before release, and the whole thing would have been a lot cheaper and had a lot less drama involved with it. So in terms of known and unknown code vulnerabilities, known vulnerabilities are things that have been discovered and widely published. And there are a few different lists of known vulnerabilities. Usually, if you hear about a known vulnerability, it has a CVE number associated with it. And these are things that reactive tools can look for. And generally, it just means that if you have a known vulnerability in a piece of software, you just have to make sure that you get the patched version of that software so that the vulnerability is no longer there. Unknown vulnerabilities are also called zero-day vulnerabilities. And these are the ones that are really dangerous, because if an attacker locates them and exploits them, there are no defenses against them. Now that you understand about the different types of software vulnerabilities, let's take a look at how you can manage them. The goal for any organization should be total vulnerability management, consisting of a two-pronged approach of known and unknown vulnerability management. On the known side of things, there are tools like Nessus that will search out for bad configurations, default authentication credentials, unpatched software, and other kinds of vulnerabilities like that. On the unknown side of things, there's basically white box and black box testing approaches. Historically, the white box approach was code review, in which pairs of developers or teams of developers would manually read through the source code and look for problems. Because modern software often has hundreds of thousands of lines of code, possibly millions of lines, automation is a necessity. On the white box side of things, there are static analysis tools that will walk through the source code for a piece of software and identify programming patterns that might be a problem. By contrast, the black box approach is a dynamic testing approach in which a piece of software, a running binary, is tested through its externally available interfaces. For any organization, you should try to do all of these approaches, both the known vulnerability scanning, the white box testing, as well as the black box testing. This will give you the best possible coverage, helping you to find the most bugs before you release a product, helping the product to be the best possible quality that it can be. However, we also recognize that a buyer organization, for example, will not have access to the source code of a product that it's purchasing, and so this is not always possible. Now let's take a look at how a typical attack occurs. We call this the anatomy of a hack. And so what I'll outline is the typical steps that an attacker will take in trying to compromise some network. So let's assume that I'm trying to break into your network. How does this happen? In the movies, I would just flip open my laptop and type madly away, and all of a sudden I'd be able to control anything in your organization. In real life, it doesn't happen that way. And in real life, there's a lot of effort and time that goes on ahead of time before launching the attack. So we call this studying and analyzing and identifying. What I'm going to do is I'm going to look at your network and try to figure out everything that's running on it. So I want to know about every piece of equipment and every piece of software running on that equipment in your network. This includes an awful lot of stuff. So if you look at a typical network diagram for even a mid-size organization, it's very complicated. It has lots of boxes in it, and every place that there's a piece of software running that takes some kind of input is a place that I could potentially attack. It's an attack vector. So if you sum up all of the attack vectors over the entire network, that's the attack surface of the network, and typically that's a very broad attack surface. Keep in mind that we're not just talking about traditional computing resources here. The attack surface includes desktop computers and laptops and the software that they're running, but it also includes things that you might not think of, like all the mobile devices that are on the network, all the switches and routers and network infrastructure, things like networked printers or networked fax machines. And then finally, in some organizations, there are ancillary things like HVAC systems that are also on the network. If it's on the network, it's going to be an attractive target for me as an attacker. So what I will do is find as much of that stuff as I can, that equipment, those pieces of software, and I'll install it into my secret hacker lab somewhere. And then in my lab, I'll try to locate all the vulnerabilities I can. And one powerful tool for doing that, of course, is fuzz testing. There are other tools as well to look for vulnerabilities, but fuzzing's very popular among attackers because it's so good at finding unknown vulnerabilities. Once I've done this analysis, I have some list of vulnerabilities in various pieces of software. Then I'll go and do additional research and see if I can exploit those vulnerabilities. And I'll develop exploits for various vulnerabilities. And at the end of this step, I've got a bunch of weaponized exploits, and I've got a kind of an arsenal that I can choose from to figure out how I want to compromise your network. Maybe I'll use one of these now. Maybe I'll save some of these weaponized exploits for later, or I'll be able to use one to attack a similar organization that has the same kind of software. Once I'm ready to go, I'll put together a plan for how to deliver the exploit into your network and how to accomplish my hacker aims. And then once I've got everything all set up, I go and I press the big red button, execute the plan, and in a fraction of a second, it's game over. I'm into your network, I'm running my own code, I can steal information, I can steal money, I can launch further attacks, I can do whatever I want to do. So you've heard that the world's full of software, and software is full of vulnerabilities. So what are the defenses that we have against these software vulnerabilities? To answer that, we're going to look at a metaphor, and the metaphor is something called the Maginot Line. And this is from history. After World War I, the French, of course, were conquered by the Germans, and after World War I, they were pretty upset, and they said, "Zut alors, never again." And so what they did was they came up with this plan for the Maginot Line. And it was intended to be a series of super strong fortifications along the border between France and Germany. We have an artist's rendering here, which it's a little fanciful. I don't think they actually had underground aircraft hangars or an underground railroad. But it gives you some idea of how elaborate this fortification was. And France did, in fact, build this Maginot Line. They spent some incredible percent of their GDP on this fortification. They used money on it that they could have used on other defenses, but they built the thing. And of course, when World War II came around, what happened? Well, France built this fortification between their border and Germany, and in a sense, it worked because the Germans did not, in fact, penetrate the Maginot Line. What the Germans did was, of course, they rolled through Belgium and went around the top of the Maginot Line, and France was again conquered in a matter of about 6 weeks. So this is actually a really good metaphor for the current state of cybersecurity and the defenses that are available against vulnerabilities. So many companies have invested a lot of money in traditional cybersecurity defenses. And when I say traditional, what I'm talking about is antivirus software, intrusion detection systems, intrusion prevention systems, and any other type of traditional cybersecurity solution. And that's fine, but the problem is these are all reactive solutions. So antivirus deals with things that everybody already knows are bad, and intrusion detection systems, prevention systems basically look for signatures of things that people already know are bad. There are vulnerability scanners, such as Nessus, that look for things that are known to be bad. And so all of these technologies are reactive technologies. They're necessary. They're a good idea, But if that's all that you're using, you're missing a lot of the picture. And so a lot of people will say, well, I spent a lot of money on this solution and my vendor told me I'm secure now. And that's great, but what we call that is faith-based security. Did you actually test? Did you verify? Do you trust your vendor? Does your vendor know what they're doing? And so what we're proposing is, instead of faith-based security, you do some testing yourself and have facts that you can deal with. And that's what fuzzing is about, really, is being able to do your own testing on whatever piece of software or device that you want and find out what kinds of zero-day vulnerabilities are lurking inside. Thank you for watching these videos. We hope you've enjoyed them. If you want to learn more about fuzz testing, visit our website at www.codenomicon.com.